Have you ever gazed at the moon and wondered about the secrets it holds? From its role in shaping life on Earth to its stunning features visible even from millions of miles away, the moon is more than just a celestial companion. It's a world of wonder, with mysteries waiting to be unraveled. Are you ready to dive into 10 incredible things about the moon? Join us as we explore its fascinating facts, ancient impacts, and surprising characteristics. The moon was formed by a massive collision. One of the most fascinating aspects of the moon's origin is its dramatic creation story. Scientists believe the moon was formed around 4.5 billion years ago when a Mars-sized object named Theia collided with Earth. This cataclysmic event ejected a massive amount of debris into space, which eventually coalesced to form the moon. Evidence of this giant impact hypothesis lies in the moon's composition. Lunar rocks collected during the Apollo missions show a remarkable similarity to Earth's mantle, suggesting that both celestial bodies share a common origin. This finding has helped scientists piece together the violent history of our early solar system. The moon's formation played a pivotal role in Earth's evolution. The massive collision tilted Earth's axis, creating the seasons we experience today. Additionally, the moon's gravitational pull helped stabilize Earth's rotation, preventing chaotic wobbling that could have drastically altered our planet's climate. While we now have a clear idea of how the moon came to be, there are still ongoing studies aimed at understanding the finer details of its formation. Space missions and advanced simulations continue to shed light on the early years of Earth and the moon's shared history. The moon's birth story isn't just about its formation. It's a testament to the dynamic and often violent processes that shape the cosmos. Understanding this dramatic event helps us appreciate the interconnectedness of celestial bodies within our solar system. The moon influences life on Earth. The moon is more than a distant companion. It plays a critical role in shaping life on Earth. Its gravitational pull is the primary force behind ocean tides, creating the rhythmic rise and fall of water levels that have been vital to coastal ecosystems for billions of years. These tides, influenced by the moon's phases, help regulate marine life cycles. From coral spawning to the behavior of fish and other sea creatures, the moon's pull sets the pace for life in the ocean. Without the moon's steady influence, these ecosystems might not have developed as they have. The moon also impacts Earth's rotation. As the moon's gravity interacts with our planet, it slows Earth's spin by about 1.5 milliseconds per century. While this seems insignificant, it has a profound cumulative effect. Millions of years ago, a day on Earth was only about 18 hours long, but thanks to the moon, we now enjoy 24-hour days. The moon's presence in the night sky has also influenced human culture, from mythology and literature to calendars and rituals. Ancient civilizations carefully observed their phases to track time, plan agricultural activities, and guide navigation. The moon's impact on life extends far beyond tides. It's a silent but ever-present force that shapes our environment, culture, and daily rhythms. Without it, Earth as we know it would be an entirely different world. The moon has a far side, not a dark side. The far side of the moon has often been misnamed the dark side. But this is a common misconception. Both sides of the moon experience day and night cycles, just like Earth. The far side is simply the part of the moon that faces away from Earth due to tidal locking. Tidal locking means the moon rotates on its axis at the same rate that it orbits Earth, causing one side to always face us. This phenomenon is why we only see the familiar features of the near side, like the Sea of Tranquility and the Tycho crater, while the far side remains hidden from view. The far side of the moon was first glimpsed by humans in 1959, thanks to the Soviet Luna 3 spacecraft. This side has a rugged, heavily cratered surface, starkly different from the near side's smoother, darker plains. The lack of Maria or lunar seas on the far side is attributed to differences in crust thickness and volcanic activity during the moon's early history. Exploration of the far side continues to provide valuable insights. In 2019, China's Chang'e 4 mission became the first spacecraft to land on the far side, uncovering data about its unique geology and deep craters that could hold clues to the solar system's formation. The mystery of the moon's far side captures the human imagination, reminding us of the unseen wonders that await exploration in our cosmic backyard. The moon is shrinking. The moon is slowly shrinking as its interior cools. This cooling process causes the moon's crust to contract, resulting in the formation of cliffs called lunar scarps. These scarps can rise as high as 300 feet and stretch for miles across the lunar surface. NASA's Lunar Reconnaissance Orbiter has captured images of these scarps, revealing that they are relatively young in geological terms, just a few 100 million years old. Some scarps even show evidence of ongoing activity, indicating that the moon is still geologically dynamic. This contraction has caused occasional moonquakes. Unlike earthquakes, which are caused by tectonic plate movements, moonquakes occur due to the moon's shrinking crust and the gravitational pull of Earth. While they are not as intense as earthquakes, moonquakes can last much longer, sometimes up to 10 minutes. The shrinking moon also provides clues about its thermal evolution. Scientists study the size and distribution of scarps to understand how the moon's interior has cooled over billions of years, offering insights into the thermal histories of other rocky worlds. The shrinking process is a reminder that even celestial bodies we consider static and unchanging are constantly evolving. The moon continues to surprise us with its ongoing activity and the secrets it holds beneath its surface. Moon dust is surprisingly dangerous. The lunar surface is covered in a fine layer of dust known as regolith. While it may look harmless, this dust is surprisingly dangerous. Lunar regolith is composed of tiny, sharp particles created by billions of years of meteoroid impacts, which have pulverized the moon's surface. During the Apollo missions, astronauts discovered firsthand how problematic moon dust could be. It clung to their suits and equipment, and even got into the lunar module, causing respiratory irritation and damaging seals on spacesuits and machinery. The jagged edges of lunar dust particles make them abrasive, posing a significant challenge for future lunar missions. Prolonged exposure to these particles could harm both humans and equipment, necessitating innovative solutions for dust mitigation. Despite its dangers, lunar regolith has potential scientific and practical applications. It could be used as a building material for future lunar habitats or as a source of oxygen through chemical processing. Researchers are exploring ways to harness this abundant resource while mitigating its risks. Moon dust serves as a reminder of the challenges and opportunities that await humanity as we prepare to return to the moon. The moon is slowly drifting away from Earth. The moon isn't as stationary as it might seem. It's actually moving farther away from Earth at a rate of about 1.5 inches per year. This slow drift is caused by the gravitational interactions between Earth and the moon, specifically the transfer of angular momentum due to ocean tides. Tidal forces create a slight bulge in Earth's oceans, which exerts a gravitational pull on the moon. This pull adds energy to the moon's orbit, causing it to spiral outward over time. Though the change is gradual, it has profound implications for Earth and its future. As the moon drifts away, its impact on Earth's tides diminishes. Over billions of years, this could lead to less dramatic tidal changes, which might significantly alter coastal ecosystems that rely on the moon's gravitational pull. Additionally, the moon's distance affects solar eclipses. A more distant moon will appear smaller in the sky, eventually making total solar eclipses a thing of the past. This phenomenon also tells scientists about the Earth-Moon system's history. By studying lunar rocks and Earth's geological layers, researchers have pieced together how the moon's gradual drift has influenced Earth's rotation and climate over millions of years. The moon's drift reminds us that even the most familiar celestial bodies are not static. They are part of a dynamic and ever-changing universe with ripple effects that extend across space and time. The moon has an atmosphere, but it's extremely thin. Contrary to popular belief, the moon does have an atmosphere, but it's so thin and fragile that it's called an exosphere. This exosphere is composed of rarefied gases, including helium, neon, and argon, which are present in trace amounts compared to Earth's dense atmosphere. The moon's exosphere is constantly being replenished by several processes. Solar wind particles, micrometeoroid impacts, and the slow release of gases from the lunar surface all contribute to this tenuous layer. Unlike Earth's atmosphere, the exosphere doesn't provide protection from radiation or support for breathable air. Because of its lack of a substantial atmosphere, the moon experiences extreme temperature swings. Daytime temperatures can soar to 260 degrees Fahrenheit, while nighttime temperatures plummet to -280 degrees Fahrenheit. Without an atmospheric buffer, there's nothing to distribute heat evenly or shield the surface from direct solar radiation. This thin exosphere still holds valuable scientific insights. For instance, studying the moon's exosphere can help scientists understand the behavior of gases on other airless celestial bodies, such as Mercury and certain moons of Jupiter and Saturn. The moon's delicate exosphere highlights the challenges of future human exploration and settlement, as well as the ingenuity required to adapt to its harsh environment. The moon experiences moonquakes. Just like Earth experiences earthquakes, the moon has its own seismic activity, known as moonquakes. These quakes were first detected during the Apollo missions when astronauts left seismometers on the lunar surface. Unlike earthquakes, which are caused by tectonic plate movements, moonquakes have different origins. Moonquakes can be triggered by the gravitational pull of Earth, meteorite impacts, thermal expansion from sunlight, or the moon's internal cooling and contraction. Some of these quakes can last for an extended period up to 10 minutes because the moon lacks the water-rich rocks found on Earth that help dampen seismic vibrations. There are 4 types of moonquakes: deep, shallow, thermal, and those caused by meteor impacts. Shallow moonquakes in particular can be quite powerful, reaching magnitudes of up to 5.5 on the Richter scale, enough to cause structural damage if humans were living on the moon. Understanding moonquakes is essential for designing safe habitats for future lunar missions. Structures must be resilient enough to withstand these quakes and other environmental hazards. Moonquakes reveal that the moon is not as geologically dead as we once believed. It's a reminder that even a seemingly barren world can have dynamic internal processes that are crucial for scientists to study. The moon has water, but it's trapped in ice. The discovery of water on the moon has been one of the most groundbreaking revelations of the 21st century. In 2009, NASA's Lunar Crater Observation and Sensing Satellite, LCROSS, mission confirmed the presence of water ice in permanently shadowed craters at the moon's poles. These craters, located in regions that never receive sunlight, act as cold traps where temperatures can drop below -400 degrees Fahrenheit. At these frigid conditions, water molecules become frozen and remain preserved for potentially billions of years. This water ice holds immense significance for future lunar exploration. It could be used as a resource for drinking water, oxygen production, and even rocket fuel through the process of electrolysis. The ability to harness lunar water would make long-term habitation and deep space exploration more feasible. Scientists are also studying the origin of this water. It could have been delivered by comets and asteroids, or formed through chemical reactions between solar wind particles and the moon's surface. Understanding its origin provides insights into the history of water in our solar system. The moon's icy reserves symbolize untapped potential for human exploration and survival, paving the way for a new era of space travel and scientific discovery. The moon might hold clues about Earth's early history. The moon is often referred to as a time capsule for Earth's early history. Because it lacks weather, tectonic activity, and a thick atmosphere, its surface has preserved ancient features and records that have been erased from Earth over billions of years. Lunar rocks and soil provide clues about the early solar system. By studying the moon's composition, scientists have learned about the bombardment of asteroids and comets that occurred during a period known as the Late Heavy Bombardment. This era shaped not only the moon but also Earth, potentially delivering water and organic compounds critical for life. The moon's surface also offers a record of solar activity. By examining isotopes in lunar rocks, researchers can reconstruct the history of the sun's radiation and its effects on the inner solar system. Additionally, the moon's relatively unchanged crust holds information about Earth's early crust and mantle. Comparing the two bodies helps scientists understand how the Earth-Moon system has evolved over time, including the dynamics of Earth's magnetic field and plate tectonics. The moon's preserved history acts as a window into our past, reminding us that studying our closest neighbor can uncover secrets about the origins of our planet and the conditions that made life possible. The moon is a celestial treasure trove of mysteries and wonders, each fact revealing a deeper connection between our planet and its natural satellite. From its drifting orbit to the water hidden within its craters, the moon is far more complex and fascinating than it first appears. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep discovering the universe's wonders with us. What makes Saturn one of the most fascinating planets in our solar system? Is it the stunning rings that stretch far beyond the planet, or the countless moons that orbit it, each with its own unique story? From mysteries hidden in its atmosphere to the incredible discoveries made by spacecraft, Saturn is a treasure trove of wonders waiting to be explored. Join us as we dive into 10 fascinating facts about Saturn and uncover the secrets of this celestial marvel. Saturn's majestic rings. Saturn's rings are one of the most iconic features in the solar system, captivating astronomers and stargazers alike. Spanning up to 175,000 miles wide, these rings are composed primarily of ice, rock, and dust. Despite their vast size, they are incredibly thin, averaging just 30 feet in thickness. This extraordinary combination of scale and delicacy makes Saturn's rings a true masterpiece of nature. The rings are divided into several sections, with the most prominent ones named A, B, and C. Each section contains countless individual particles ranging from tiny grains to massive chunks of ice. These particles reflect sunlight brilliantly, creating the shimmering effect we see through telescopes. This striking beauty has earned Saturn the nickname, the Jewel of the Solar System. Scientists believe the rings formed relatively recently in cosmic terms, possibly 100 million years ago. They may be the remnants of a shattered moon or comet that was torn apart by Saturn's immense gravity. The ongoing interaction between the planet's moons and its rings creates stunning patterns, including waves and gaps, adding to their dynamic appearance. The Cassini spacecraft provided unprecedented insights into the rings during its mission. By diving through the gaps and analyzing their composition, Cassini revealed intricate details about their structure and origin. The findings not only expanded our understanding of Saturn, but also offered clues about the formation of other planetary ring systems. The rings may not last forever. Over time, they are slowly disintegrating as particles rain down onto Saturn's surface. This fleeting nature adds a poignant layer to their beauty, reminding us of the ever-changing universe we inhabit. The hexagonal storm. At Saturn's North Pole lies a bizarre and mesmerizing phenomenon, a massive hexagon-shaped storm. This geometric wonder was first observed by the Voyager spacecraft in the 1980s and has since been studied extensively by missions like Cassini. Spanning about 20,000 miles across, this storm is large enough to engulf Earth twice over. The hexagon's perfectly symmetrical shape is a result of Saturn's turbulent atmosphere. Scientists believe it forms due to a combination of jet streams and rotational forces unique to the planet. The storm rotates at an astonishing speed, with winds reaching up to 200 miles per hour, creating a spectacle of swirling clouds. Inside the hexagon, a giant hurricane-like storm rages at its center. This storm has a massive eye, nearly 50 times larger than a typical hurricane's eye on Earth. The striking contrast between the central vortex and the surrounding hexagonal structure adds to its otherworldly appearance. One of the most intriguing aspects of the hexagon is its changing colors. During Saturn's long seasons, which last about 7 Earth years each, the storm shifts hues, from a golden yellow to a pale blue. This change is likely due to the interaction between sunlight and atmospheric particles, providing valuable insights into the chemical composition of Saturn's atmosphere. The hexagonal storm remains one of the most mysterious and captivating features of Saturn. Understanding its formation and dynamics could unlock new knowledge about atmospheric phenomena, both on Saturn and other planets, including Earth. Titan, Saturn's largest moon. Titan, Saturn's largest moon, is a world unto itself. Larger than the planet Mercury, Titan has a dense atmosphere and a surface unlike anything else in the solar system. Its thick orange haze, composed mainly of nitrogen and methane, conceals a landscape of rivers, lakes, and seas made of liquid hydrocarbons. This alien world has fascinated scientists since its discovery. Titan's surface temperature is a frigid -290 degrees Fahrenheit, yet its geology bears a striking resemblance to Earth's. Rivers carved by methane rain flow into lakes and seas, creating a hydrological cycle similar to the water cycle on Earth. The Cassini-Huygens mission provided groundbreaking data about Titan. In 2005, the Huygens probe descended through Titan's atmosphere, becoming the first spacecraft to land on a world beyond Earth's moon. It captured images of icy plains, pebble-like structures, and evidence of underground reservoirs of water and ammonia. Titan's potential for life has sparked intense interest. Beneath its icy crust lies a subsurface ocean of liquid water, a key ingredient for life as we know it. The combination of organic molecules in its atmosphere and water below the surface makes Titan a prime candidate for future astrobiological missions. Exploring Titan further could not only reveal the secrets of this moon but also provide clues about the origins of life in the universe. It remains one of Saturn's greatest wonders, a reminder of the diversity and complexity of our solar system. The fastest winds in the solar system. Saturn is home to some of the fastest winds in the solar system, reaching speeds of over 1,100 miles per hour at the equator. These powerful winds are driven by the planet's rapid rotation, which completes a full spin in just 10.7 hours, the shortest day of any planet in the solar system. The winds create striking patterns in Saturn's upper atmosphere, including bands of alternating colors. These bands are composed of ammonia and methane clouds, with the lighter bands rising higher and the darker bands sinking lower. The interplay of these layers forms the planet's iconic striped appearance. Storms frequently erupt in Saturn's atmosphere, further showcasing the planet's volatile weather. One of the most famous is the Great White Spot, a massive storm that appears roughly every 30 Earth years. These storms can grow large enough to encircle the entire planet, leaving visible scars on its surface. The winds also play a crucial role in distributing heat across Saturn. Despite being nearly 900 million miles from the Sun, the planet radiates more heat than it receives. Scientists believe this heat comes from its interior, where helium rain generates energy that fuels the extreme winds and storms. Studying Saturn's winds provides valuable insights into the dynamics of planetary atmospheres. It helps scientists understand weather patterns on gas giants and their smaller cousins, the exoplanets orbiting distant stars. Saturn's winds remain a fascinating example of the raw power of nature. Saturn's gravity and low density. Saturn is a planet of extremes, and its gravity is no exception. Despite being the second largest planet in the solar system, Saturn's gravity is only slightly stronger than Earth's due to its low density. Saturn is so light that it could float in water, assuming you could find an ocean large enough to hold it. The planet's density is less than 1/10 that of Earth, primarily because it is composed mostly of hydrogen and helium, the lightest elements in the universe. This unique property gives Saturn its characteristic shape, a slightly flattened sphere due to the centrifugal force generated by its rapid rotation. Gravity plays a crucial role in shaping Saturn's moons and rings. The planet's immense gravitational pull has captured dozens of moons and influenced their orbits over billions of years. Saturn's rings also owe their dynamic structure to gravity, with moonlets within the rings creating gaps and waves that add to their striking appearance. Scientists have studied how Saturn's gravity interacts with its moons to understand tidal forces. For example, these forces create tidal heating in moons like Enceladus, causing geological activity such as geysers. This phenomenon demonstrates how gravity can shape the geological and atmospheric features of celestial bodies. The study of Saturn's gravity provides valuable insights into planetary formation and evolution. It also helps us understand how gas giants develop their unique characteristics, adding another layer of intrigue to this magnificent planet. Enceladus, the ocean world. Enceladus, one of Saturn's smaller moons, is a tiny world with a big secret. Beneath its icy surface lies a global ocean of liquid water, making it one of the most promising places to search for life beyond Earth. This discovery has transformed Enceladus into a focal point of astrobiological research. The moon's surface is covered in a thick layer of ice, which reflects nearly all sunlight, giving it a dazzling white appearance. At its south pole, geysers shoot plumes of water vapor and icy particles hundreds of miles into space. These plumes are evidence of the subsurface ocean and have been a treasure trove for scientists studying the moon's potential for life. The Cassini spacecraft made groundbreaking discoveries about these plumes, detecting organic molecules, salts, and hydrogen. These ingredients suggest that hydrothermal vents at the ocean floor could provide the necessary conditions for microbial life, similar to those found in Earth's deep oceans. Enceladus's geysers also contribute material to Saturn's E-ring, one of its faint outer rings. This connection between the Moon and the planet highlights the dynamic interplay of celestial bodies within the Saturnian system. Exploring Enceladus further is a top priority for future missions. By studying its ocean and geysers in greater detail, scientists hope to uncover whether life exists in this distant, icy world. Enceladus is a reminder that even the smallest moons can hold the greatest mysteries. Saturn's magnetic field. Saturn's magnetic field is one of the most powerful in the solar system, second only to Jupiter's. Generated by the movement of metallic hydrogen within the planet's core, this magnetic field creates a protective bubble around Saturn known as a magnetosphere. The magnetosphere extends far into space, trapping charged particles and shielding the planet and its moons from harmful solar wind. This protective barrier also plays a role in creating Saturn's stunning auroras, which light up the polar regions in dazzling displays of ultraviolet light. Saturn's magnetic field is unique in its near-perfect alignment with the planet's rotational axis. This unusual feature has puzzled scientists, as it defies current theories of how magnetic fields are generated. The study of Saturn's magnetism could provide new insights into the internal dynamics of gas giants. The interaction between the magnetic field and Saturn's rings creates fascinating phenomena. For example, charged particles from the rings can influence the structure of the magnetosphere, while the magnetic field, in turn, affects the behavior of the rings. This dynamic relationship offers a glimpse into the complex interplay of forces shaping the Saturnian system. Understanding Saturn's magnetic field is not only key to unraveling the mysteries of the planet itself, but also to comprehend the broader mechanisms governing planetary magnetism in the universe. The seasons of Saturn. Saturn's tilt of 26.7 degrees gives the planet distinct seasons, similar to those on Earth. However, because Saturn takes nearly 29.5 Earth years to complete one orbit around the Sun, each season lasts more than 7 Earth years, creating long and dramatic transitions. During its summer and winter solstices, the planet's poles are bathed in continuous sunlight or shrouded in darkness, creating stark contrasts. These prolonged periods of light and shadow affect the behavior of Saturn's atmosphere, with storms and cloud formations changing in response to seasonal shifts. The rings also reflect these seasonal changes, appearing brighter or dimmer depending on the angle of sunlight. During equinoxes, when the sun shines edge onto the rings, they cast thin shadows on the planet's surface, creating breathtaking sights captured by spacecraft like Cassini. Seasonal variations extend to Saturn's moons, particularly Titan. Methane lakes on Titan's surface change in size as the seasons progress, offering a glimpse into the moon's unique weather cycle. These observations provide valuable data about how Saturn's environment evolves over time. Studying Saturn's seasons helps scientists understand the effects of axial tilt and orbital dynamics on planetary systems. It also highlights the intricate connections between the planet, its atmosphere, and its moons, painting a vivid picture of a world in constant motion. Saturn's core and internal heat. Deep within Saturn lies a mysterious core that has long intrigued scientists. Unlike the solid cores of rocky planets like Earth, Saturn's core is likely a mixture of rock, metal, and ice surrounded by a dense layer of metallic hydrogen. This unique composition is the result of the planet's immense pressure and low temperature, creating conditions unlike anything we experience on Earth. The core is estimated to be about 10 to 20 times the mass of Earth, but its exact size and composition remain uncertain. This uncertainty stems from the difficulty of observing a region buried beneath thousands of miles of dense gas. However, data from the Cassini spacecraft has provided clues, suggesting that the core may be more diffuse and less defined than previously thought. Saturn generates more heat than it receives from the Sun, a phenomenon linked to its core. Scientists believe this heat comes from helium rain within the planet. As helium droplets form in Saturn's upper atmosphere, they sink toward the core, releasing gravitational energy as heat. This process is a key driver of the planet's internal energy and contributes to its dynamic weather patterns. The heat from the core also affects Saturn's atmosphere, influencing the formation of storms and the movement of wind currents. It provides a stark contrast to the planet's frigid outer layers, where temperatures can drop as low as -288 degrees Fahrenheit. This interplay of heat and cold creates the unique atmospheric dynamics observed on Saturn. Understanding Saturn's core is essential to unraveling the secrets of giant planets. By studying its structure and energy sources, scientists can learn more about the processes that shaped not only Saturn, but also other gas giants and exoplanets in distant star systems. Saturn's role in shaping the solar system. Saturn is not just a celestial marvel, it plays a significant role in the architecture of our solar system. As one of the most massive planets, its gravitational pull has a profound impact on the orbits of nearby celestial bodies, shaping the paths of asteroids, comets, and even its own moons. The planet's gravitational influence is believed to have helped stabilize the solar system during its early formation. By capturing and redirecting stray objects, Saturn likely prevented many collisions that could have disrupted the development of the inner planets, including Earth. This protective role has earned Saturn the nickname of a cosmic guardian. Saturn's interaction with its moons adds another layer of complexity. Tidal forces between the planet and its moons, such as Enceladus and Titan, drive geological and atmospheric activity. These interactions not only shape the moons themselves, but also contribute material to Saturn's rings, creating a dynamic system of mutual influence. The planet's position in the solar system also affects the Kuiper belt and the Oort cloud, regions filled with icy objects at the outer edges of the Sun's influence. Saturn's gravity, combined with that of Jupiter, helps steer comets toward the inner solar system, where they can be studied in greater detail. These icy visitors often provide valuable information about the early solar system and the building blocks of life. By studying Saturn's role within the solar system, scientists gain a deeper appreciation for how planets interact with one another and their surroundings. Saturn's gravitational dance is a reminder of the intricate and interconnected nature of our cosmic neighborhood, highlighting the planet's enduring significance in the grand scheme of the universe. Saturn is more than just a planet. It's a cosmic masterpiece filled with wonders that stretch the boundaries of our imagination. From its majestic rings to its mysterious moons and dynamic storms, Saturn continues to inspire awe and curiosity. If you enjoyed this exploration, be sure to like, share, and subscribe to InnoVision Tech. Don't forget to hit the bell icon to stay updated with our latest videos. Until next time, keep exploring the universe with us. Ever wondered what makes Venus one of the most fascinating planets in our solar system? From its mysterious backward spin to its surface temperatures that could melt lead, Venus is a world of extremes and surprises. Did you know it's considered both Earth's twin and a potential warning about our planet's future? Join us as we uncover 10 mind-blowing facts about Venus, exploring the secrets of this enigmatic world and what it tells us about our place in the cosmos. Venus rotates backward, a planet in reverse. Venus does something truly unusual. It spins backward compared to most planets in the solar system. While Earth rotates on its axis from west to east, Venus spins from east to west. This retrograde rotation means the Sun rises in the west and sets in the east on Venus, a concept that's hard to imagine for those of us used to Earth's patterns. The reasons for this backward spin remain a cosmic mystery. Scientists theorize that a massive collision with an asteroid or protoplanet during Venus's formation may have flipped its axis. Another possibility is the influence of gravitational forces from the Sun and other planets, gradually altering its spin over billions of years. What's even more fascinating is that a day on Venus is longer than a year on Venus. It takes about 243 Earth days for Venus to complete one rotation on its axis, but only 225 Earth days to orbit the Sun. This creates a bizarre dynamic where the planet's surface experiences incredibly long periods of daylight and darkness, leading to extreme environmental conditions. Venus's slow and backward rotation contributes to its thick, stagnant atmosphere, as the planet lacks the Coriolis effect that creates dynamic weather patterns on Earth. This strange spin offers clues about the chaotic early days of planetary formation and how celestial collisions can shape a world's destiny. Venus is the hottest planet in the solar system. Despite being the second planet from the Sun, Venus is the hottest planet in our solar system. Its surface temperatures reach a staggering 900 degrees Fahrenheit, hot enough to melt lead. This intense heat is caused by a runaway greenhouse effect, where Venus's thick atmosphere traps solar energy and keeps the planet perpetually scorching. The atmosphere of Venus is primarily composed of carbon dioxide, with clouds of sulfuric acid reflecting sunlight. Instead of cooling the planet, this creates a heat-trapping cycle that has turned Venus into an inferno. Even spacecraft that have landed on Venus could only survive for a few hours before succumbing to the extreme temperatures and crushing pressures. What's intriguing is that Venus may have once been much cooler and possibly even supported liquid water on its surface. Some researchers suggest that billions of years ago, Venus might have been Earth-like, with conditions that could have supported life. However, as the planet's greenhouse effect intensified, its oceans boiled away, leaving the barren, hostile world we see today. Venus serves as a stark reminder of the power of greenhouse gases and the potential consequences of climate change. By studying Venus, scientists hope to gain insights into Earth's atmospheric dynamics and how to prevent a similar fate on our planet. Venus has super-rotating winds. Beneath its serene appearance, Venus is home to some of the most extreme weather conditions in the solar system. The planet's thick atmosphere is whipped into a frenzy by super-rotating winds that reach speeds of up to 250 miles per hour. These winds circle the planet in just 4 Earth days, far outpacing Venus's sluggish rotation. The phenomenon of superrotation is not fully understood, but scientists believe it's driven by a combination of solar heating, the planet's dense atmosphere, and its slow rotation. The winds are strongest in the upper atmosphere, creating a high-speed jet stream that encircles the planet. Near the surface, however, the winds slow down significantly, creating a much calmer environment. These winds also drive the movement of Venus's thick cloud layers, which are composed of sulfuric acid droplets. The clouds reflect sunlight, giving Venus its bright and shining appearance in the night sky. This reflection is why Venus is often called the morning star or evening star, as it's one of the brightest objects visible from Earth. Venus's super-rotating winds challenge our understanding of atmospheric dynamics and highlight how different a planet's weather systems can be from those on Earth. Studying these winds could provide insights into atmospheric phenomena on other planets and even exoplanets beyond our solar system. Venus has no magnetic field. Unlike Earth, Venus lacks a significant magnetic field, leaving it exposed to the full force of solar wind and radiation. Magnetic fields are usually generated by a planet's molten core and its rotation, but Venus's slow spin and internal structure prevent it from producing this protective shield. Without a magnetic field, Venus's atmosphere interacts directly with the solar wind, leading to the gradual loss of lighter elements like hydrogen. This loss likely contributed to the disappearance of water on Venus, as solar radiation broke water molecules into hydrogen and oxygen, with hydrogen escaping into space. The lack of a magnetic field has also made Venus a prime target for studying how planets interact with their star. By observing Venus, scientists can learn more about the effects of solar wind on a planet's atmosphere and the conditions that could affect habitability in other worlds. Interestingly, Venus's atmosphere is so thick that it still retains most of its gases despite the absence of a magnetic field. This resilience provides a stark contrast to Mars, which also lacks a magnetic field but has a much thinner atmosphere. The differences between Venus, Earth, and Mars highlight the complex interplay of factors that shape a planet's evolution. Venus's surface is a volcanic landscape. The surface of Venus is dominated by volcanic features, making it one of the most geologically active planets in the solar system. Over 80% of Venus's surface is covered in volcanic plains, with vast lava flows, towering mountains, and massive calderas. Venus is home to some of the largest volcanoes in the solar system, including Mont Mons, which rises nearly 5 miles above the surrounding plains. Unlike Earth, where volcanic activity is driven by tectonic plate movements, Venus's volcanism is thought to result from upwelling plumes of molten rock beneath its crust. Recent studies suggest that Venus may still be volcanically active today. Observations from spacecraft have detected changes in the planet's surface temperature and composition, hinting at ongoing eruptions. This activity could be responsible for the sulfur dioxide variations observed in Venus's atmosphere. The volcanic landscape of Venus offers a window into the planet's geologic history and provides clues about its internal structure. By studying Venus's volcanoes, scientists hope to better understand the role of volcanism in shaping planetary surfaces and atmospheres. Venus's fiery surface is both a testament to its violent past and a reminder of the dynamic processes that continue to shape our solar system. Venus's atmosphere is a crushing hellscape. The atmosphere of Venus is a place of unimaginable extremes, making it one of the most hostile environments in the solar system. Composed primarily of carbon dioxide with traces of nitrogen and sulfur dioxide, this thick atmosphere creates pressures 92 times greater than Earth's at the surface. It's equivalent to being nearly a mile underwater on Earth. The crushing pressure isn't the only challenge. The atmosphere contains clouds of sulfuric acid that blanket the planet, reflecting sunlight and giving Venus its bright appearance. These clouds not only make it impossible to see the surface from space, but also contribute to the planet's searing heat. Despite these extreme conditions, scientists are fascinated by Venus's atmosphere. Some studies suggest that microbial life could exist in the upper cloud layers, where temperatures and pressures are more Earth-like. This possibility has sparked interest in sending more missions to explore the atmosphere and uncover its secrets. Understanding Venus's atmosphere is crucial for planetary science, as it provides a glimpse into what happens when a greenhouse effect goes unchecked. By studying Venus, we gain insights into climate dynamics that could have implications for Earth and other planets. The atmospheric hellscape of Venus is both a warning and a wonder, showcasing the planet's ability to challenge our expectations about what a world can be. Venus once had oceans, but they boiled away. Venus may seem like an inferno now, but evidence suggests that it once had oceans of liquid water. Billions of years ago, Venus's conditions might have been similar to Earth's, with a cooler surface and the potential to support life. As the sun gradually brightened over time, Venus's temperatures rose, causing its oceans to evaporate. The water vapor, a potent greenhouse gas, traps more heat in the atmosphere, creating a runaway greenhouse effect. This led to the boiling away of its oceans and the transformation of Venus into the scorched planet we see today. One of the key pieces of evidence for past water on Venus comes from the ratio of deuterium to hydrogen in its atmosphere. Deuterium, a heavier isotope of hydrogen, is more likely to remain in the atmosphere when water is lost. Venus's atmosphere has a much higher deuterium to hydrogen ratio than Earth's, suggesting significant water loss. Understanding Venus's climatic history is vital for modeling the evolution of habitable environments. If Venus had liquid water and potentially habitable conditions, why did it change so drastically? These questions drive ongoing research and missions aimed at uncovering the planet's past. The story of Venus's lost oceans is a haunting reminder of how fragile habitable conditions can be and how planetary environments can evolve over time. Venus's surface is young and renewed. Unlike the Moon or Mars, which are littered with craters from billions of years of impact, Venus's surface is relatively young, with an average age of about 300 to 500 million years. This youthfulness suggests that the planet undergoes periodic resurfacing events that erase its geological history. The primary mechanism for this resurfacing is thought to